little bit. So hydrogen-powered cars, we're using this reaction. You're reacting hydrogen with oxygen to produce water. That heat released in your exothermic reaction is what's producing it, producing the power to drive the car. So exciting. Where does the hydrogen gas come from? Typically, it's coming from some kind of petroleum or non-renewable source. So we've got a new chemical reaction that we can go through and evaluate here. I want you to go through and calculate the KEQ. Is this reaction product or reactant favored at this temperature? And then write out the KEQ expression. If you're going to calculate the KEQ, you probably needed to write out the expression anyway. I just went through and regraded, or not regraded, but did the retakes for quiz 3. And I'm noticing a lot of people are just skipping kind of the given information by like writing out what the K should be. And I think skipping that has resulted in the loss of points that you otherwise would have gotten if you'd just written that expression out. So work at your tables to figure this out. If I don't really feel like people are working at the tables, we'll go up to the boards as well. I don't really have any problems with either of those options. So start working on it, and I'll work on getting quiz 3 retakes back. All right, so my reflex as soon as I see KEQ means I'm immediately going to go through and say K is products over reactants. I've got this equation, so I would immediately start launching into the concentration of my carbon monoxide, my H2. What's the big thing I got to watch out for?
Liquids and solids.
Yes, liquids and solids, because they don't show up in the KEQ expression. Say that again?
With your first and second orders?
It's not orders in this case, but
it.
the exponents.
Yeah.
Okay, so we would have to drop those exponents in because H2 is to the third, or 3 of them. We got to make sure that we cube that one. And then we would divide it by the concentration of our reactants, because everything was a gas. It's all going to show up in the expression. So that would be my natural immediate reflex. Okay, within that reflex, that's not the greatest reflex. Because do I know any of those concentrations? No. So I can't actually solve for the KEQ this way. Right? To a certain extent, it helps out because the very end of this does ask for the right of the KEQ expression. Okay? So I did do the work that I need. I just did it in the wrong order. Okay? So how am I going to solve for the KEQ if I don't have the concentrations? Okay, so I understand where you're going, playing a little chess move out there, which is cool. What equation are you referencing to figure out your K from your delta G? As in
the delta
G equals negative RT ln K? Did I do that right?
Yeah.
Okay. So we would need delta G to solve for that. We don't have delta G, which means we have to do another step backwards. Okay, within our effectively chess move, if I'm going to keep running that. Now we're looking at delta G equals delta H minus T delta S. Do we have the delta H?
Yes.
Do we have the temperature?
Yes.
Do we have the delta S?
Yes.
Yes. Okay, so now with that information, we can start moving our process forwards. Our delta H was 205.9. We want to make sure that we include our units because that's a silly place to lose points. Sometimes again. So our delta H is 205.9 kilojoules per mole. I personally like the fraction format and think the slash format is dumb. Does anybody know why we have that slash format? Computers. That's literally it. Okay? And if we argue it's not even computers, it's freaking typewriters, because it's really hard to type a fraction, okay, on a typewriter, so you invent the slash so you can have the fraction within a single line. Okay? All of your work is not done on a freaking computer, so put it in a format that actually makes logical sense to go through and use. So you should be writing it out in this proper system. Okay? If we navigate into the next thing, we've got our T. T should be in what units? Kelvin. So if we wanted to get real lazy, we could say 273 plus 25 instead of doing it separately, which either is fine. Of course, I shifted it, and I needed to shift it even more. And then we'd bring in our delta S. Okay, our delta S was 214.7. By writing in the units, hopefully, this calls attention to the fact that we are in improper units, or rather units that aren't going to work out well, because I've got kilojoules versus joules. I can choose to go any which direction because it's not even asking for the joules. Okay, so we can decide to convert this to joules or kilojoules, and it's really not going to matter that much of a deal. Okay, if we're playing out our chess moves, what was the whole point of solving for the delta G?
Plug it back into the Gibbs reconfiguration model.
To solve for K from our delta G equals negative RT ln of K, right? What's R?
Constant 8.314.
8.314 joules. Okay, so if that's going to go in as joules, we're probably going to keep our joule unit and not our kilojoule unit. Does that make sense? Okay. So however you want to go through and do that, I already forgot the number, 2059, and then what I need, 2 more zeros? Joules, okay? And then for that, for the record there, what do I need is usually something that I screw up, so this is actually something I would write out the work for. If you're confident in that conversion process, you can run it however you want to run it. I'm not going to look for that unit conversion work. What I'll look for is that the unit has changed, and it has changed appropriately. Does that make sense? Okay, we can now go through, plug that all in. What do we get for delta G? What?
I got negative 141,000.
So I'm hearing negative 141,000 joules. If you're getting 0.0, something weird is going on there, because that's not even a joule to kilojoule issue. Do we get a second on the joules? On an answer for this?
I got a positive,
I got yeah.
like positive 142.
Positive 142? Did you get positive or negative?
Negative. Maybe I did something wrong.
I'm hearing 2 positives. Got positives? Okay. Oh, you've got confirmation on that? Did I screw up something else? Make sure our signs. So good thing to double back through and check. Okay, this is actually one of the reasons why I like to include my signs on this. Delta H is positive. Delta S was positive. Okay, so that should be positive. That should be positive. Okay, so I'm not missing a minus sign anywhere else. Say again?
The reason I got plus is because I divided kilojoules by 1,000.
So yeah, as long as you do it right, I won't track for it. But I personally know that I struggle with that, and so I would actually try and solve that out. Okay, so we're looking at positive 141, 142, something like that. Okay, joules. Now how do we go through and solve for our K? This was our delta G. So now we got to navigate back to the expression that we set up here. Okay, I personally would go through and take that RT ln of K and start to shuffle things around. Ln of K equals delta G over RT, negative sign, make sure we got that negative in there. K equals E to the negative delta G over RT. That looks real ugly. Okay, trying to sub in those numbers, particularly a freaking long number, 141,000, okay, is going to be a mess. But you should still be putting that all in. Okay, so you could probably do E negative 141,000. Why do we need the joules? Why do we need the units? So that we can call attention to the fact that we're going to cancel the units from our R, mole, Kelvin. So our joules can cancel. Our temperature was, anybody actually solve for it? I should have known that. 298 Kelvin. And so what do we get for a K? Pause. Let's actually not even think about that yet. From the delta G, what does the delta G tell us? Ooh, it tells us information about spontaneity, right? Because it's positive, we know it's not spontaneous. If it's not spontaneous, which side of the equation is favored? The reactants, which means what should the magnitude of K be? Less than 1. So when we go through and get our K, what are we getting for K? 1.3 times 10 to the negative
25, if I did that right.
25. We did have an issue there, but you're getting secondary confirmation.
Okay.
That's what I got.
Okay. So we now have the K. So we know our reaction, the product versus reactant. We didn't have to evaluate the K to get to it. The delta G gave us that information. So we have internal feedback suggesting that that's true. So the K and the delta G at least jive with each other, which means our calculation more or less is potentially right. Okay. We also have the KSP or the KEQ expression written out for us, where I technically started, and we now have kind of all the pieces put together. Make sense? Okay. If you note, we've got lots of writing kind of all over the place. I do try and track your work wherever it's at, even if it's nonlinear. Okay, so as long as it's there, I can try and piece it together. To that end, for sure, I think personally on quiz 4, there wasn't a whole lot of space for some of those questions. If you need scratch paper, that's okay. You just have to ask. And I'll get you more paper so you can draw stuff out there. Okay, and if you're going to draw stuff out on the scratch paper that you want graded, please make a note in the question so that I know to reference that instead of having to look everywhere for it. Questions?
What did you say about the product or reactant favored?
So deciding whether it was product or reactant favored, I said there was 2 places we could look. We could look at when we solve for delta G. The delta G is positive, so it's a non-spontaneous reaction, which means it's reactant favored. Right? Because the delta G told us it was reactant favored, that gave us a tip back to K. Our KEQ should be less than 1 because we should have larger reactants than we should have products. And we see that also coming into play. So our K is less than 1, our delta G is greater than 0. Both of those things suggest reactant favored. Make sense? Okay. So still looking at that same system, we want to draw an energy profile diagram. So this was one of the things we started to discuss when we looked at kinetics. I remember with kinetics we talked about the speed of the reaction, and that speed was dictated based off the activation energy. The activation energy was the difference in energy between our transition state and our reactant. If we're going to look at an energy profile diagram, that's what we're concerned about. It's what's the energy versus your reaction coordinate as you progress from reactant to product. So with the information you have from the previous question, we know it's reactant favored. You should be able to go through and draw an energy diagram for this. Okay? After that, you now have follow-up questions. Okay? If you want to increase the amount of hydrogen produced, what could you do? What could you do to make the reaction faster? Okay? Again, blue box, you should start working on your tables, talk to each other, see if you can come up with some kind of conclusion about those, and I will try and wander. Appreciate the yes. So if we're going through and looking at the energy diagram that we very quickly, crudely started, okay, this isn't a complete energy diagram. For our reaction coordinate, you have to go from reactants to products. So we have to establish where the product was. Okay, this diagram was really just setting up to remind you back to the kinetic conversation we had. And when we talk about kinetics, okay, that was talking about the transition state, activation energy, and the speed of the reaction, all that fun stuff. So we do get some questions coming into play about speed, but first we got to address our energy profile diagram. Okay, so within the diagram, what do we know has to be true about our products? And I think it's gross, so I'm going to redraw it. What do we know about our products?
But they're not favored.
That they're not favored. What does that mean?
Lower than the reactant.
If they're lower than the reactant energy, they're actually favored. Okay, lower energy is more stable. So if our products are not favored, our products have to be higher in energy than our reactants. Okay? Where are we going to see that mathematically show up? If we look at the difference in energy between our product and our reactant, that difference in energy, depending on the units that you're using officially on this thing, delta G, or you'll sometimes see it as delta H, is your products minus reactants. If your product energy is higher than the reactant energy, what's the value going to come out to be? Positive, which is exactly what we saw when we looked at delta G. Delta G was positive, and our delta H was also positive given this context. So we should be seeing the product energy higher in energy than our reactants. If we're going to finalize the energy diagram, we have to pass through some kind of transition state. Okay. In this process, we are making a pretty nasty assumption behind this. That assumption is that how many steps are involved? 1. Okay. Given no other context, that's the assumption that we should go through and make. If you went through and drew a bunch of humps in between, I might complain, but I'm definitely not going to take off points because you don't have information to make any assessments about what's going on with the number of peaks across the top. Does that make sense? So we've got our energy profile diagram. It doesn't ask to do any labels. You'll note that I already started to put some labels in there. The primary reason for starting to put those labels in is that, remember, part of this is supposed to be review. And one of the big lessons that I would argue that comes out of 152 is an energy diagram. So you should be able to fully label the bejesus out of it so that you know where everything is, okay? And what it overall means. So if we're looking at a delta G that's positive, our product energy is higher, okay? This would be what kind of a reaction? This would be an endothermic reaction, okay, which we'll come back to as an important term. Okay, we could look at the activation energy. The activation energy is between our reactant and our transition state. Okay, that's the activation energy for the forward reaction. Because we're in 152, we know that we also have reverse reactions. So we could look at the activation energy for the forwards or the backwards. The backwards makes sense because B looks significantly different than F. Okay. What other pieces of information could we label on this? We got a transition state. I thought there was something else, but I think that's it. Okay. When we're looking at an energy diagram, this is great. We've labeled all of this, but this is only for the endothermic. Are there other forms of chemical reactions? Yeah, there's exothermic. What does the exothermic look like? So as part of your review, you should be leaning into what those other things are and how that would change your overall diagram. Does that make sense? Okay. For the sake of this question, we've kind of gutted as much as we could out of our energy diagram so we could follow on to the next thing. If we wanted to increase the amount of hydrogen produced, what could we go through and do? Okay. So one idea was to add heat. How is adding heat going to increase the amount of hydrogen?
The reactant and adding more.
So there's the kind of important statement that I think a lot of people go through and miss. If we're talking about this being an endothermic reaction, what does that mean? Heat is required. It is a reactant. So I could go back and modify my energy diagram, or sorry, not my energy diagram, my equation, to go through and add the heat term. And if I increase the concentration, quote unquote, of one of my reactants, what does the equilibrium do? It shifts to make more products. Okay? So increasing the heat in this case helps me out, increasing the temperature, because that's one of my reactants that shifts to make more hydrogen. That works great for an endothermic reaction. If it's exothermic, where's the heat? On the product side, when you increase the heat, it shifts away from it. So what we're leveraging is Le Chatelier. Does that make sense? Okay, so modifying the temperature is great. You just got to make sure that you're tying it back to the concept correctly. Okay, the heat is going to affect both the rate of the forward and the reverse reaction. It's going to affect both. It's just going to affect the forward more because the product energy is already so high. Okay, that activation barrier isn't going to have much of an effect when we change the temperature. When I have a much larger barrier, adding more heat is going to have a much greater overall effect. Kind of make sense? Okay. What else could you go through and do?
Add the CH4.
Add more of one of the reactants. Just like adding heat, we could also go through and say, well, I'm going to add more CH4. Okay? That will equally work to help push. Okay? We could also equally add more of the H2O. But if you add more methane and more water, do you get a larger percentage of the H2? No. Okay? All you're going to do is get to the same equilibrium. You'll have more, but you'll have more of the reactants. Your ratio isn't affected that much. So if I'm trying to increase just the production of hydrogen by minimizing my usage, I increase one of the things. Okay? Heat's technically not really a reactant or product when we kind of go through those. So you could increase the temperature and methane and leave your water constant. That's going to have a doubling effect of increasing the amount of hydrogen produced. Does that make sense? Okay. What we're leveraging in that approach is the Chatelier's principle. How else could you do this? Pick some numbers, throw them into an equation, and determine the concentration of hydrogen. Okay? And if you're like, that sounds like a lot of work, that's because it is. Okay? But once you're used to the process of doing that, the calculation becomes a little bit easier and more straightforward. I would argue you don't need to do that unless you're asked to do it. Okay? Lean into the use of Le Chatelier. Kind of make sense? Okay. What could you do to make the reaction faster?
Add a catalyst.
Add a catalyst. Okay. What is a catalyst going to do? That catalyst changes the mechanism of how this reaction works. And by changing the mechanism, the transition state drops. If the transition state drops, the activation barrier also drops, and we get a faster reaction. So the catalyst is one of the best things that you can do to make the reaction faster. Okay? Make sense? What's up? Are you good? Questions about what's up there? Okay. So we could also go through and produce hydrogen gas from water. We typically don't do this because the amount of energy input that we've got to run through to do that is more than we would need from petroleum. So the reason why we'd be using solar is because we have that energy, so we would leverage it and take advantage of it, even if it's less overall efficient, within the system. So we've got this reaction set up in front of us. Okay, to go through and do this, we're looking at now our, and I've got to try and fix my terminology for this. Those E values are our reduction potentials. How do we know those are reduction potentials? What does reduction mean? Adding electrons or gain of electrons. So if we go through and look at our equation, where are the electrons appearing in both cases? On the reactant side, we're adding electrons in. So we could be extra clear and call these E red. Okay. And perhaps that's why I keep calling them cell potentials. They are not cell potentials. The cell requires both the reduction and the oxidation. Okay. So we're looking at the reduction potentials for each of those equations. If we look at our overall equation, we're now asked, is it spontaneous? Okay. What's oxidized and what's reduced? The original equations given are all reduction. okay? Which means nothing's going to happen. One of them has to be oxidized. So the question is now going to become, which one is oxidized? Okay? Deciding how to run that, if you're talking about cell potentials, we find the most negative, we flip it and run for the best, right? Okay? In this case, we've got to be a little bit more careful because we have to match the overall equation. Make sense? Okay. Spend some time to work on it, see what you come up with. So, deciding if the reaction is spontaneous, what information do we need? We're talking about spontaneity. Okay, we would need the E cell. Okay, or what would be the other thing we could look for to decide spontaneity? Delta G. Okay, both of those are potential things that we could be using to evaluate. I'll come back to the other part of that to figure this out. So if we're now going through and looking at the information given, we're not given information that allows us to easily solve for delta G, but we are given reduction potentials, and we could manipulate the reduction potentials to get us our E cell. Okay? So let's go through and determine our E cell. So the best approach that I would see is trying to make those equations match your overall reaction. Okay? Instead of trying to say your E cell is and I already don't know what it is. What is it? Anode minus cathode? Okay, so apparently I've memorized it better than I thought I would. Okay, generally speaking, for me, that's a 50-50 memorization. Okay, deciding which one's the anode or the cathode, I still have to flip the equations. I still have to do all that work. So memorizing that equation of which one I have to subtract from the other isn't a useful thing to go through and memorize. Okay, it really isn't. Okay, and so instead what we should focus on is what's going on within the chemistry. I need this overall equation. So a couple people looked at that overall equation and then looked at the reduction potentials. Okay, the first thing that people saw, that I didn't, but that's fair, they went and saw that water is a reactant. When we go through and look at our reduction potentials, where do we have water? It's on the product side, which means I have to flip that equation. Okay? That equation is going to need to be flipped so that I can get my water on the reactant side. Okay? When I go through and flip, everything else is going to spin around. I guess I'll put on all the phases. I don't technically need the phases for this one, plus 4 electrons. When I flip that equation, I'm no longer looking at a reduction potential. I'm looking at an oxidation potential. Because I've flipped it, I will flip the sign on it to be negative 123 volts, 1.23 volts. Okay? What do I do to the other equation? Well, I don't need to flip it. Okay? How do I know I don't need to flip it? I already flipped one. That's the first hint. The other hint, I've got hydrogen as a product. In my overall equation, where do I want hydrogen to be? Product. That's the only place hydrogen shows up. It needs to stay in that format. Okay? Before I get too excited about rewriting that one, what I would immediately do is zero in on the electrons. We're looking at 4 electrons. That's 2 electrons versus 4 electrons. Those are not going to cancel. Okay? So before I go through the rewrite, what I'm going to acknowledge is that I have to multiply that top equation by 2 so that I can get those 2 electrons up to 4 electrons. I'm not flipping the equation, so we'll leave it as is. I like to align the arrows on top of each other. Okay, particularly if my brain is mush because I can't see where my arrows are. And then I would backtrack out, so 2 times 2 is 4 electrons, plus 2 times 2, 4H plus, aqueous, plus 2 H2 gas. I didn't flip that equation. I'm still looking at the reduction potential here because I didn't do anything to it. That's still going to come in as 0 volts. So I don't have to change any signs. We don't have to multiply our cell potentials. I don't have a good answer for that. Still don't. Okay, but you don't multiply your cell potentials. You leave those alone. Okay. Now what can I go through and do? In the tiny remaining space that I've got left, I would add my 2 equations together, and I would get my overall result. Okay. As I do that, depending on my mood at any individual instant, I may go through and look at the individual half reactions to see if there's any commonalities. So 2H2O shows up only on the reactant side, so I'm okay to write 2H2O. Okay. The next reactant I see is 4H plus. That also shows up on the product side, which means they can cancel out. The electrons, 4 electrons, also cancel out. I have nothing else on the reactant side. O2 gas plus 2H2 gas. Now what's my cell potential? I just add the two cell potentials together and I get negative 1.23 volts. Okay. I'm recognizing that the cell potentials change signs when I flip them. Otherwise, I just add them up. Depending on wherever your comfort lies, pick a method. Don't do both. Okay? Because if you do both, you're going to end up multiplying the negative to get rid of it and then bring it right back. Okay? Does that make sense? Okay, we now have our overall reaction. For those people that were struggling because they were like, it didn't balance, that's because the original reduction potential for our oxygen was not actually balanced. Okay? 2 oxygens, and how it was written was just 1 water. That clearly doesn't balance. There was just a typo within that formula. Okay? So we now have our overall reaction. We know what's going on with each of our cell potentials, or what our cell potential is. So now we can answer the question about, is it spontaneous? Is it spontaneous? No. Does it make sense for it to not be spontaneous? Yeah. That's why we're using solar energy to cause the reaction to happen. We have to bring in that input of energy to force this chemical reaction. So it shouldn't be spontaneous. That makes a lot of sense. Okay? What's oxidized and what is reduced? That oxidized and reduced can come back from just knowing those terms. Okay? Those terms being LEO is loss of electrons, is our oxidation. The loss of electrons means our electrons must be a product. I've already labeled it within the potential. So my oxidized thing would be my water molecule. What's my gain of electrons?
Your hydrogen.
Okay. Looking at this system, it's going to be H plus, but didn't I cancel that out? What's going on? Okay. So what is oxidized and what is reduced? So the thing that was reduced was hydrogen. It had to be hydrogen. But I canceled that from the equation, didn't I? It's the hydrogen coming from the water molecule. So the individual molecule of water is both being oxidized and reduced. The individual elements are what's changing within our oxidation and reduction. That's kind of neat. Okay? What's the solar energy used for? It's to actually force that chemical reaction to happen. Okay? Because it's a non-spontaneous reaction. To make it happen, I need the energy to force the water to split. Okay? To really zero in on what's happening as far as oxidized and reduced, you could look at those half reactions. Again, that becomes challenging. Okay? The half reactions give it to you. If you look at the overall equation, it looks really confusing because there's only one reactant, but that's where you would determine the oxidation numbers for each of the species. And when we look at water, the oxidation number for hydrogen is +1. For oxygen, -2. When I go to the product, what's the oxidation number for oxygen? 0. So I'm going from a -2 to a 0. What happened? Right? Okay, and the plus minuses are always nasty. Okay, we're looking at a loss of electrons. And if it lost electrons, what happened to it? It was oxidized. Isn't that what we were saying? Okay, if we go through and look at the hydrogen in the product is 0. We went from a +1 to a 0. That was gaining of electrons. Okay, so the oxidation numbers can also kind of help us navigate through that system. Okay. The questions themselves, I would argue, are a little bit vague because we're saying what is oxidized, what is reduced. Okay. In the overall equation, what is oxidized? Water. What is reduced? Overall equation, water. Okay, so this is where we run into that weird dilemma. I would argue if you're going to be asked what is oxidized and what is reduced, what you're going to see is what element is oxidized, what element is reduced, to add an extra layer of clarity behind that. Does that make sense? Questions? Okay. Wrong button. Oh, that's the end of this slide set. So this slide is trying to get you to think back and review backwards. What determines your reaction rate? This is kind of what we talked about, and you all said you didn't want to talk about, okay, on Monday, right? When I said, when we have kinetics, what does that mean? Kinetics was our rate. Okay, what's determining that rate? We could go through and jump to kind of one of the big conclusions was the rate equals our reactance. This is really just looking at kind of the definition of what the rate is. And we've got our M and N. I'm showing them to be M and N, so they're non-standard variables. Those are orders. Those orders must be solved experimentally, okay, or defined based off of a mechanism. Okay. That gives us the answer of what rate is, but what's controlling it? Why would I expect to see the reactants in the rate, but not, say, the products? I have a feeling this is going to come back and bite me, but I've got an analogy that can work on this. Okay? Why would I expect to see the reactants and not the products? Why should the reactant concentrations appear but not the products? Okay, if we're talking about populations, right, to make populations, what has to happen? Okay. Things have to come together to produce kids so that we can adjust the population. Okay? And if we're looking at, it's totally going to bite me, but we're going to work on it anyway. Okay? The things have to come together. The reactants have to come together. Do the kids involve the reaction of coming together? No, they're after the fact, right? Okay? So the coming together is the reactants coming together. Okay? The products shouldn't affect the chemical reaction, okay? For a couple reasons. Usually, they aren't there when you're making the products. If we're going to take to a chemical reaction, we mix the reactants. Are there any products yet? No. So what's going to control the speed of the reaction? Just the reactants. That's why the reactants should show up. Okay? And if you want to extrapolate the whole involvement of the kids, you can use varying theories behind that, and I'm not trying to make it like bad, just too many kids, so we stop the reaction, right? That kind of thing. That's where I was going with that. But ultimately, the parents, our reactants, have to come together. They have to collide, right? And if we're talking about that collision, this is where we bring in collision theory. Okay, and so when we're talking of our collision theory, we're talking about temperature. Why would temperature affect the number of collisions? Okay, they're moving more, and if they're moving more, we increase the odds of actual collisions. But just because they move more, does that mean you form product? No, because I can have two particles collide and not make a product. Okay, what else has to be true? They have to clear the activation energy, which the temperature can help do. Okay? Additionally, it's not just collision, it's the proper orientation of said collision. Okay? So there's a bunch of kind of secondary things that fit into that puzzle, and that's where we have collision theory. Okay? If we go through and look at our rates, we've got temperatures, we've got pressure. Pressure is the amount of particles within that volume, okay, which is effectively the same thing as concentration. Okay? And we can look at catalysts, and catalysts will speed our reaction along by helping to bring those reactants together. Okay? So if we're going to look at our reaction rates, okay, we've got our rate expression, we've got our orders. Those orders dictate those things. When we talk about all the other aspects that come together with collision theory then goes through and says that we can kind of pull out of K some useful information. We can figure out something about the activation energy. We can figure out something about the orientation. Okay? How do we get that information out of K? Because if that's stuck in K, how do I get the stuff unstuck? I would have to know the relationship between those. What is the relationship? Yeah, unfortunately, that's all I remember about it too, so good job. It's our Arrhenius equation, which is K equals A negative EA over RT. I think that looks reasonable. Okay. We've got a negative sign in there. That as soon as I drop a negative sign, it's going to cause anxiety because I don't know if I'm remembering that it belongs there or not. Okay. So that for me would be something I'd want to make sure is on my equation sheet. Theoretically, all the equations are given to you on your exams. A good thing to kind of, or on your final quiz, a good way to kind of check that is look at the different versions of the quizzes that you've got and look at the equations already listed. Okay. I can't guarantee it, at least not yet. Maybe I can post an announcement about it if I go through and look at the final quiz, and I would bet it's just a copy-paste of all the equations that were given to you on quiz 1, 2, 3, 4 are dumped into the final quiz. I would bet. That makes sense to me. Okay. A lot of things make sense to me and aren't real, so like my invisible friend. Are we done yet? Okay, this slide makes me a little nervous because it brings in the equilibrium constant into this. I wouldn't like to bring the equilibrium constant in yet because the equilibrium constant is defined differently. Okay, yes, it has a relationship back to the activation energy and our rate constant. Okay, but we do have to remember they're solved differently. Okay, how does KEQ come into play? What is KEQ? Okay, it's our products over the reactants. Okay, within that, you can see exponents show up. Those exponents, little p and little r, would be the coefficients from the balanced equation. Different than our rate law expression, because the rate law is now those orders. Okay, so even if these blanket equations were given to you, you're not going to be told the meaning of those pieces. So I would argue a cheat sheet would be useful to be like, oh, this number I can't just pull out of an equation. This one I can. Does that kind of make sense? How is KEQ related to our rate constants? Where'd the equilibrium constant come from? What does it mean to be at equilibrium?
Where it doesn't go back and forth. You have the same amount of products and reactants.
You don't have the same amount of products and reactants because that means it's 1. And we've seen multiple cases. In fact, every case we've looked at, K has never been 1. It can be, but we've never seen it as 1. So it's not the same amount of products as reactants.
Forward and reverse reaction occurring at the same rate.
There it is. The forward rate and the reverse rate are equal to each other. Okay? Once we define that and we now rearrange those pieces, and again, this is something I would have to solve for, but I think it's our rate constant of the forward over the rate constant of our reverse is equal to our KEQ, being capital K. Does that vaguely ring bells? Okay, and again, I might have that backwards. Okay, I would have to derive what that formula was. Okay, so that's how the rate constants are tying back to K. Rate constant, it's an active running reaction. Things are changing all over the place. Okay, once we've achieved equilibrium, okay, our concentrations are still changing, but they're changing in a way that when I make a change on one side, the other side also counteracts, so that we're not seeing a net change at all. Okay, dynamic. Kind of, sort of? Okay, so where does this then potentially come into? Oh, I have no idea what I just clicked. You jerk. Where this can come into play is looking at things that like solubility. Okay, we could also look at it with KAs and all that kind of fun stuff. Okay, so within the solubility is probably the big one that it's going to come back and bite you because we have to watch out for some certain aspects. So we've got 2 questions here. Fire away. See what you can come up with. Put it together. So with only 3 minutes left, we got to talk about some things within this, some kind of important stuff. So if we're going to take a look at magnesium carbonate, okay, we're talking about these as being KSPs. That's going to start as a solid. That's going to turn into magnesium ion plus the carbonate ion. Those should then be aqueous. The dilemma that was just kind of brought up, and it just dawned on me that I see this as potentially a problem, is that I would argue you should know what those ion charges are. I don't think you've ever been asked to memorize those things. And if you've not been asked to memorize those, how are you going to know what those charges are? I don't have a good answer for that, other than you should have been told to memorize them. Sorry. The first one is a little bit easier, because if you get your periodic table, one of the things that you could very quickly do with your periodic table is identify the columns and their ionic charges. So group 1 ionic charges are +1, group 2 +2. We usually skip over group 3 and 4 because they're not common. Okay, if they're in an ionic compound, that's a little bit different, but they're kind of variable. Nitrogen, so we're looking at group 5 is -3, -2, -1. I believe we did talk about those charges and what those common ionic charges were, because we talked about them trying to look like a noble gas. Does that vaguely sound familiar? Okay, so we've talked about that, but again, the context of your past classes is that you didn't need to memorize it. You have to know those are ions. I genuinely don't know how to approach that. I will say one potential out, which I was talking with the people up at the front. You are told off of, I believe, a slide in Unit 3 that you're responsible for recognizing certain complex ions. Okay? Recognizing them as a complex ion versus knowing what their charge is a little bit different. Okay? I would argue if you don't have those complex ions memorized, you should put that into your cheat sheet, so that when you see carbonate, you know that carbonate, or you don't even have to know that it's carbonate, but that when you see CO3, you know that's a -2. Right? And magnesium would be a +2. This is technically an equilibrium, so it should go backwards and forwards. If we look at the next equation is even more challenging. Okay? Because silver's not sitting in a common column or a common family that would allow you to know that charge. And phosphate is a super rare, not super rare, but a more rare than carbonate ion is as far as exposure, which means it's going to be even harder to memorize through practice because you wouldn't have seen it. When we go through and do this, you're looking at 3 silver ions, aqueous, plus our phosphate ion, aqueous. Okay? This becomes really, really important when we talk about trying to establish what your K expression is. So your K expression is your products over reactants, okay? But we have to remember we can only do it for our aqueous and our gases, which means our K expression for the magnesium carbonate is just going to be the magnesium ion times the carbonate ion. When we go through and look at the silver phosphate, it's going to be our silver ion to the 3rd power, that's a big deal, times the concentration of our phosphate. Okay? The KSP has to do with the solubility of that individual ion. So if we're looking at a smaller value, less stuff is dissolving. So we could sort of look at which compound is more soluble by just kind of looking at the magnitude of those KSPs. I'm a little hesitant on that, particularly as it came to, I think that's quiz 3, because when you went through and did quiz 3, there was one question that was like, calculate the molar solubilities, and then it said which one had the greater concentration, and if you just leaned into the magnitude of the KSP, you got it wrong. Okay, so for determining which one is more soluble, you should actually solve for the molar solubility. Okay, I know nobody seems to like ice tables. Tables are, what is it? What is what people say these days? Goats. Okay, and they should be gone through and used. Okay, our initial concentrations, okay, for our silver and our phosphate, okay, are going to come in at 0, but what's going to happen is you're going to start to dissolve some. Okay, those need to go up. As they go up, the other one would go down. Okay, the concentration isn't really going to have much of an effect on the reactant side. So this is where you can use kind of whatever variable you're trying to solve for. I tend to solve for X. I'm noticing a lot of people use S. I'm going to assume that's something that Alex was potentially throwing at you. Okay, but you just need to deal with a variable. If the silver nitrate goes down by X, that's how much dissolved. That X is your molar solubility. Okay, or S, whatever you're asking for. It's how much of that thing dissolved. What is the phosphate going to go up by if this one goes down by 1 or by X? It's going to go down by the exact same thing because it's a 1-to-1 relationship. When we go through and look at the silver, that's not 1-to-1, which means that's not plus X, that's plus 3X. Okay? The point of the ice table is to organize that flow so that you can kind of track it, so that when you now go back and look at your K expression, here, you could now sub in. The silver ion is 3X cubed. Okay? The phosphate was X. You could then go through and continue that on. 3 cubed is 27. Okay? X cubed is X to the third times X, X to the fourth. You could then go through and sub in, or not sub in, but realize that that was your KSP, 8.9 times 10 to the negative 17, and you could solve for X. The X that we defined, we picked around our molar solubility. Okay, why? Because we wanted to solve for that. Right? But I could have said the silver went up by X. And if the silver is going up by X, the silver phosphate needs to go down by 1/3 of X. Okay, so you just have to make sure you define what your variables are and then manipulate them accordingly. Okay? So watch out for that. What I'm seeing a lot of people do for this kind of question is doing this. That was their work. Here's the equation, no KSP, and then immediately trying to plug things in. Okay? And what happened is that you did something like that and you left off the third. Okay? Or you left off the 3 in front of the X. Okay? So without having that ice table there to actually track your work, you're trying to just jump to the answer of the problem, and that's where things backfire, is that you're missing pieces that the ice table would force you to slow down through. Okay? That's the point of the ice table, is to track work. That is it. Okay? With that, we're done. So I'm